the Twitch delay. Okay, I believe we are live. Make sure I have audio. I didn't check that. All right, we're good. So today is November 26, 2024 here at ASU. And we are halfway through microarchitecture exploitation. So let's see where we're at. So people got to start actually working on the microarchitectural exploitation. From what I could tell, it's kind of lived up to its reputation. Yeah. People are enjoying it, and it makes tons of sense, and GDB solves everything, right? And I'm kind of surprised that this meme talks about level 4 misbehaving. Typically, it's actually level 5 that people will complain about, because the first 4 levels actually are not speculative at all. It's just a CPU cache side channel that you have to take advantage of. Where level 5 is typically the hardest, considered the hardest level out of the first half of this module. Because when you try and do speculative execution, you end up with this scenario here, where you're like, okay, I understand what I need to do. I need to train this branch. I'm going to execute this program, and we're going to branch, go this path. We're going to do it 3 times. Okay, the CPU's trained. And then we're going to do something else. And then hopefully the CPU speculatively executes what we want. And I tried to stress on Tuesday or Thursday that this is a race. So you can trade it and then execute the thing that you want the CPU to do, and you can still miss it. Yeah, people agree that 5's a tricky one like that. And so you need to do this many times for every value or every index that you're trying to leak, because you may or may not actually trigger that race inside the CPU. Now, this is arguably the hardest module you're going to have in this class, although the next one definitely isn't easy. So all of that extra credit that you built up in that nice, 110% that a lot of people are sitting at, you're going to cash in on that now, because now all of the hard stuff runs through the end of the semester while you've got your finals, and it's time to cash in on the extra credit, because it does get kind of doom and gloom here. So this guy here, when the server is busy, you will have a much harder time pulling off these microarchitectural exploits, right? Now, it's still really weird, right? And it doesn't make any sense, and you can't reason about it, but it's at least kind of smooth, right? But when the server is busy and it's under load, for instance, there were some people that were trying to do some of this, I think, last week, Sunday, which is when 365 had a deadline, and so there's 600 students writing stuff. Every one of those people are executing stuff on the same CPU cores that you're trying to exploit, and their stuff goes into the same cache that you're putting stuff into. And their memory accesses will flush out things that you are putting in the cache. And so it is always better to try and pull off these exploits when the CPUs are under lower load. In general, people hold that opinion. They hate this module, but it's important that you go through it, because either you pulled it off and then it was super cool, or you have some idea of how hard it is and kind of the understanding of how hard it is. Other people have realized that maybe it makes more sense here to cash in on memes and extra credit. As someone who was like doing well, and then you kind of run into these last 2 modules, if you didn't get the extra credit early, it's going to be a rough couple of weeks. But if you did post the memes, it does make it quite a bit easier to get an A in this class, right? That is by design, as I said at the beginning of the course. Somebody said, yeah, they just had to wait for less than 50 people on the server. So you can't take that number on the actual Dojo website as an absolute number for a few reasons. Now we're multi-node. So the number that you see there is split across multiple hosts. I don't think 50 is that many when you split that across. I think we have like 3 hosts right now, if I remember right. And so that's not that busy, but definitely when there's 300, 400 students that are all spamming things, that'll cause you some grief. Now, I didn't show anyone micro sleep, but it seems to be the prevalent way that people try to synchronize levels 1 through 5. I mentioned scheduled and I mentioned nanosleep. Microsleep is just a libc wrapper around nanosleep. You're functionally doing the same thing, except because it's a wrapper around a syscall, there's going to be more memory accesses. In theory, this will decrease your likelihood because there's more things in memory being touched, which means there's more noise in the cache. And so you're causing yourself more problems that you don't need to have. But for the people that showed me they were using that, there was a way to make it work. Ultimately, what you're doing is you're just looking at these timing things and trying to make sense of this data. That's kind of the key of the whole concept. Level 7, I guess it may not have been clear, but level 7 is a different type of side channel than the first 5. Levels 1 through 5 have you write a speculative side channel attack as a level 5, so you're essentially doing like a Spectre V1 attack. Level 6 is just this little menu thing that everyone just kind of brute forces because it makes me sad. That's the reality. That is supposed to teach you about page faulting. Because if you try and speculatively access a page that isn't actually backed by physical memory, you'll get bad data. That's the whole trap of that level. Is you have to cause a page fault on all of those pages. Otherwise, the data that you'll get from your timing data will be garbage and mean nothing because you're not actually going out to physical memory, physical RAM. But the level 7 requires you to write a prefetch timing attack. And that is very different than what you're doing in, for instance, levels 4 and level 5. And so if you just kind of blindly try to apply the same technique that you had in levels 4 and 5, yes, you're going to seg fault. Because in levels 4 and 5, you are timing accesses to virtual memory addresses that are mapped within the process, or via shared memory, but they're mapped within your process. In level 7, what the challenge is asking you to do is find where in virtual memory is this mapped region. And so if you try and access something that isn't mapped, you get a seg fault. So you have to use a different technique, but it is covered in a pre-recorded lecture video. Just like grace conditions, if you wrote a horribly inefficient solution, you are welcome to run it for, I believe, up to 6 hours, as the dojo eventually does time out. However, a reasonably well-written solution for all of these should dump out a flag within a minute or so. And I think other people have came to that same conclusion. For the first couple levels, you could just end up with a cursed core. So levels 1 through 5 do randomly pin your process to a CPU core. It pins the challenge process, and then when it forks off, your exploit code is pinned to that same core. Okay, the challenge just does this for you. That's to make sure that all of that code is running on the same core that shares the same cache. Now for levels, I'm going to guess 8 and 9, 8, 9, 10, somewhere around there. I think 8, 9, 10. Those are also Spectre-based exploits. I don't believe those challenges pin the CPU for you. So if that's something you want to do, you should do that. Because otherwise, the challenge could run on one core, your exploit's going to run on another. They don't share a cache. Measuring timing is going to be a bad time because you're not actually measuring that cache hit. Logistical things. I mentioned this. My Discord availability over holiday break here is going to be hit and miss for Thanksgiving break. And then next week, Friday, typically I hold office hours. I am not going to hold office hours the following week, Friday. I'm going to try and do like a makeup thing. I'll do it on Thursday. I'll let you guys know next week, Tuesday, when I see you next. But I definitely am unavailable next week, Friday. Just so you know, if there is a day that you guys like, let me know. We'll deal with it. Now, I recognize that some of you are in this position, right? Next week, which is now this week. is a holiday. You guys have worked really hard on this, right? So you can have an actual break. Now, I did say in office hours, like, hey, if you guys gripe a lot, I'll move this checkpoint. Like, we'll see. But here's the problem. I was a student, right? And I know if I said this before break, you guys wouldn't have worked hard on it. All right. I know you said some mean things and you dunked on me, and that's fair. All right. I'll take the hit. But what I'll do what I'll do is so only about half the students reach the checkpoint that just passed here as of last night. For half the students that are solving the challenges in the module, most of the checkpoints do get completed by most of the students that are completing things. Like, it's an anomaly. And I get it because it's a hard module. So we'll move the deadline. Hopefully I typed this right. The deadline for the module will be the December 16th. It'll be the end of the semester, right? The checkpoint, I'll give you guys an extra week. So that does still run up against a holiday or Thanksgiving weekend there, right? Because it'll be the Monday after Thanksgiving break. But hopefully you guys worked really hard this weekend. So it's really like I just have to do one more challenge and it's not the end of the world, right? And you can still get that checkpoint. Is that fair for everyone? You're not happy about that. You're shaking your head. You're like, no, the due date got moved. I have more time.
I shake things as a yes.
Oh, okay. All right. Yeah. Oh, okay. Yeah. I did like this meme, not calling out any individual users, but we got it's really tiny font here, but send init extension, send try wait extension, and then they're reaching for it, and then I am blocked on a semaphore, which is exactly what happened there, right? I was going to do it, but I was like, I know if I say it too early, you guys will do it to yourself. So hopefully you forgive me for that little bit of deceitfulness there. It was for your own good. With that said, the system exploitation module will still launch this Friday in the middle of Thanksgiving break. I don't care if you do it or you don't, right? It's due at the end of the semester, but we'll keep everything exactly as scheduled. As of the launch there, all assignments for this course should be in your gradebook. Somebody asked on the Discord if that means that what is on the grades page is your course grade. As far as I'm aware, the answer is yes. There's still that survey that I claim I'm going to send out for extra credit. You can score, I think I said 1% course extra credit for filling this out. I'd love to say it's anonymous, but it can't be if I'm going to give you extra credit. Where I'm just going to ask, hey, how's the course? What do you think? What could be improved? So, yes, final exams, final projects, Microarch, it's all spooky and hard, but I will try and make this as smooth as I can for you guys. Any logistical questions as far as what it looks like between now and a grade getting posted? All right, good. It's the one thing I don't think there should be confusion about. Demo plans. So I talked about a side channel speculative attack, like using the cache on Tuesday. Thursday, I didn't demo it, but we talked quite a bit about Spectre. The third thing that is in this module, as far as a microarchitectural side channel attack, is Meltdown. Now, Meltdown works very similar to Spectre. It's still a speculative timing attack, but what you are kind of leaking is across a different domain. And so we can take a look at that. Unless you guys had something in particular you wanted to try and some path you wanted to send me down. What do you got?
I want to could talk more about Spectre V2.
Okay.
Demos for that. That's if you could just like talk in general on how we could have. What's the situation where we could use Spectre V2 to give out any useful links?
So the question for Twitch This is why you got to ask these things on Discord, man. I would have prepped one. I had some time earlier today, and I was like, what do I think I'm going to talk about? Meltdown sounds fair. And so I stole my own demo from my lecture videos. So the difference between Spectre V1 and Spectre V2, can anyone tell me what it is? Not you, somebody else. All right, what's the difference between Spectre V1 and Spectre V2? All you gotta do is read the slide.
Direct branches.
All right. Yes. So Spectre V1 takes advantage of conditional branches. This is where we have that compare instruction, and the CPU has to guess: are we going to perform this conditional jump, or are we not? Right. And that's where this whole idea of training comes in. And this is Spectre V1 is like the classical example of what Spectre is. Most of the time when people talk about Spectre attacks, it's Spectre V1. Spectre V2, as somebody said here, very astutely, they identified that Spectre V2 takes advantage of indirect branches. What's an indirect branch? Yeah, all right, I'll give you this one.
Like a jump that during runtime. So during compile time, you don't know which jump you're going to have. So
Okay, so the statement for Twitch was it's a jump that I know at runtime that I don't know at compile time. And that's true. That is what an indirect branch or an indirect jump is. So if we think about
all jumps like indirect jumps, because if we use variables, we don't know what value that's gonna hold. So it's like we won't know if that jump is taken unless we run it with the value.
but that's conditionally, like you'd have one of a couple choices, but that's indirect jump can be anywhere.
Anyway,
So like if I have assembly and it calls something, right? I'm going to call a function. Do I know where that function is?
yes.
Yes. Is at that location, am I ever going to call something else? No. What if I have something where I'm dynamically computing a location that I'm jumping to? Right? We can poke at this challenge because I know I could scribble something together, or we can find one. Yes. Says there's an indirect call. So let's open this bad boy up. Somebody says they don't know. I know, I ask the tricky questions, man. Make it real hard. All right, we'll pull up IDA here. Let's go down this road. So these later levels, you might think, hey, this is spooky, because now if you paid attention, this is a kernel module. It should actually be easier for you to do that. How like levels 1 through 5, we had the shared memory and the semaphore that you needed to use to trigger the challenge to execute something. It's not meant to be a big secret here, so I'm gonna spoil a little bit of it. The way these kernel modules work is we have our friend ioctl, right? And so we can perform an ioctl on this kernel module to cause it to then execute or do something. And so you can write userland code that will then call ioctl to force this kernel to execute. Very similar idea, except instead of it all being in userland with shared memory and a semaphore, we are now using ioctl to trigger this behavior running inside of the kernel. All right. So this looks kind of weird. All right. Victim, mfence. So what am I looking for here? Like, I'm looking for an indirect call, right? I'm looking for some call that I can trigger. Have you looked at this guy? Okay. Do you have an idea of where this issue is? I don't know. So like I can look at it, or you can guide me in the general direction.
I have it somewhere in the else block. So it should be somewhere in the else block.
Somewhere in the else block. Okay.
If just result is just -1, that's not very useful.
Because there's definitely some reversing involved here, right? To understand how these values are being used. If private data, we're going to call this victim function on safe flag private data 0 and then the address of target, where target is gadget. What does victim do? Return junk. Junk must be very important. Anded with this is a dereference of target, and it's calling it on. This is good old IDA shenanigans here, but we're calling the pointer that is stored at RBX, right? So IDA makes it look like a giant mess, which in my experience is what IDA does. But this target is a function that is being called on these arguments, some address, shared memory, and input. And so Spectre v2 works very similar to Spectre v1 in the sense that you're training a predictor on what is going to be executed when it doesn't know something, right? But in Spectre v1, you are training the CPU what to do on that conditional jump, just an if-else. With Spectre v2, you're training a different part of the CPU. Because this call to target, is this an if-else? What if target's 1? What if, then we're jumping to 1. What if target's 1337? We'll jump to 1337. Could it be 1338? Sure, why not? Right? So this particular function call can go to a bunch of different places. And there's a different part of the CPU that keeps track of where have we indirectly gone from here. Very similar logic. It's not the nice, simple state machine, but we still don't need to train it a bunch of times. Our strategy is still the same thing. We execute it one way a bunch of times, and then we change it up. And what this allows us to do is jump or call into a function that we originally weren't supposed to, speculatively, with these arguments. And so our question then becomes, well, where does this thing normally go? Like, where do we want to train it, and what do we want to try and pull off? Right? Well, since this tells you that there's an indirect call in Spectre v2, does Spectre v2 still involve a hash timing sidechannel? You say no?
Jump.
So, right, but we're jumping to an address concretely or speculatively? Does speculatively executing anything do anything in the concrete world? No. The only thing that we can influence by speculatively executing something is the cache, right? It is something else in the CPU, some other microarchitectural element. And so if I want to leak information, I probably want to speculatively execute something that I can then observe via a timing sidechain. So what can we do here? Let's see. So victim, char star adder, char star shmem. Shmem hopefully means shared memory. And then I have input. We're going to CL flush. So this is flushing the address where that pointer is so that that pointer isn't in the cache. And that makes some sense, like that we would do that, because that makes sure that the CPU doesn't have an idea of what's there. So it forces this target call to be slow. And it has to be slow because that address that is stored there is not in the cache. We force it out. It's just part of the challenge design. So then it is, what is target? Now here's target, there's target. Target by default is gadget. Do I control gadget? Sad day. Okay. And what is gadget? Okay, gadget is going to access shared memory. And that's an interesting number. Have we seen this number before?
Sounds
It's page. And I told you all of these speculative like cache timings here are going to be a multiple of a page to just make life easier for you, right? So we can take this guy, which is a page, and it is a accessing shared memory times a page times the value that is at adder. All right, we're starting to get somewhere, right? We're starting to see these pieces that we saw in like Spectre v1. It's just now, instead of there being a branch that is executing it, it's going to be a function address. It's going to be this call that we need to influence. So where does the flag come into memory here? Probably in a net.
I think it's on the top one.
It's in a net. Right there, baby. All right. So when we load this kernel module, we open the flag, we read the memory from that file descriptor into this flag variable. It looks like we have a little typo there. All right. If you're unaware, a while back, there was a typo on the belts that we ship out. There's still a couple. There's only a few left. A few collector pwn.college belts, which this harkens back to. So we read into this flag. We have this safe flag here that says pwn.college. And then we create the device. So we're reading into flag. Where's flag and safe flag? Bam. Flag. Safe flag. Where are you? You're 128 character array. Flags 120 character. Where is this? Okay. So safe flag is just right behind flag. That I can buy. So those are right next to each other, which is an interesting thing to recognize in memory. So how do I influence the execution of this thing? You said you looked at it, right? I don't want to like sit here and rev this whole thing. But what can I control here?
I believe the private data. That's something that's what we pass on to our output.
Private data. So private data on the file for these kernel modules, and you probably saw this back in the kernel module, is just a reference to like a global that we can then touch on at different entry points. If we consider like a init module as an entry point here, there's probably, oh no, init module doesn't have anything, but device open would have a file which also then has private data. And so there's this private data member is kind of like this universal global thing that we can access and define how we want. It's also worth noting that this kernel module, did you have to do this in kernel? You have to mmap? Well, today, you have to learn how to mmap. So this very similar to how we could call open on something, you can call mmap on a file to map a file into your virtual memory space from userland. Just like how some of these had in the kernel module, we had device read or device write. Right? This is the functionality that would be triggered if you were to call mmap on the file that is or on the file descriptor that's returned from opening this kernel module. And so one of the ways that you can interact with this kernel module is by mmapping this file in, and what it's going to return to you is this private data, right? And so that is another communication channel that you have. So now I know that I can call ioctl to make this thing do something. I may not fully understand what's going on, but I see some of the pieces there. And then I can mmap to get access to memory that I can see in userland and the kernel is interacting with. Yes.
So when we mmap on a file descriptor, we get access to the private data in our userland. Is that
the statement was when we mmap on a file descriptor, I get access to that in userland.
Yeah.
The answer is yes.
That's is that what is it?
That's what that kernel module is doing. So if we take a quick look here at mmap, mmap is kind of a Swiss Army knife function where it does a lot of different things. And depending upon what you're doing with it, some of them may be just null or -1 to indicate, hey, I'm not utilizing that functionality, right? Like what you've probably seen earlier in the course is you can set the address to be null, you set a length, you set some permissions like, hey, I want this to be a shared region of memory or a region of memory that's just for me. The address can be a hint. So I believe we've had several challenges where we're like, oh, there's something at 1337, right? We're going to put your shellcode at hex 1337. The way that the challenge is doing that is it's calling mmap with this first argument as 1337, which is a hint saying, hey, I'd like this region of memory that I'm requesting to be allocated at the virtual memory address hex 1337000. Your length is how much memory you want, needs to be multiple of page. Your protections are read, write, execute, blah, blah, blah. And then your flags are indicating whether it's just like private shared, whether you want to pre-fault it. There's a bunch of stuff if you read the man page. But then you get these other two arguments here at the end, which are kind of weird. And for the most part, we haven't had to use them in any of the earlier stuff. So I believe by default, file descriptor would be -1, and then offset is 0 because it doesn't matter. But what you can do with mmap is you can say, pass a flag to say, I want to map a file. And then you include the file descriptor that you've opened from that file. And instead of having to open a file and then read it into a region of memory, what you can do is you can call mmap and just be like, all of the contents of that file, just throw it here in virtual memory.
Okay, so that's like okay, so if I mmap a file descriptor in, and if I change the contents in the map region, would that be saved to the file?
If I map the contents of a file to the shared region, is it updating the file? I honestly don't know. I think the answer is no.
Yeah, because when we mmap from a kernel module and change the private data, the kernel module should be able to see those.
Well, that's a different question. Okay. The first question was, does it change the file that's on disk? Right? There's a big difference between is changing something in memory reflective and getting written to disk on the file system. I'm pretty sure the answer there is by default no. So someone wiser than me can correct me there. But for this kernel module, we can open this thing and we get a file. Does this file that is the kernel module correspond to something that's written to disk? No. So we're already like that first question doesn't really matter here, right? Doesn't matter if this is flushing to the file. right? But when I open this file, we trigger device open. Device open internally inside this kernel module. I don't have to know what vmalloc user is. We can just loosely say, okay, whatever. It's some kind of malloc function, right? It's mallocing a bunch of memory, and it's putting the pointer at private data. So that is the extent of what I need to know. And I think you can reasonably get that from this right here. If you wanted to look that up, great. Now, when I call mmap on that file, it is returning, it looks like it is remapping that kernel virtual memory address, which is at the file pointer, and then exposing that to us via mmap. Right? Now, when I look at mmap, and we look at those flags, we see that there's a number of different ways I can map memory. I can map memory shared, where this is reflected in other processes. I can map this private, where that memory is just me. Now, if your question is, if I write to this memory, can the kernel see it? Sure. Shared memory. But do you think this challenge just lets you like write the flag to shared memory and you read it? Like that's what we did for you?
Thinking no.
Right, yeah. If it was that easy, we wouldn't be having this discussion and it wouldn't be in microarchitectural exploitation, right? Because then you're just like, how does shared memory work? But if we think back to my great rant on Thursday about how cache side channels work, right? We take a byte of the flag, we use that to index into some array to then read something, right? That is what we would get the challenge to do in like level 4 and level 5, right? What we needed to have and what the challenge did for you was it injected shared memory into you. And we're just like, oh yeah, this magic happened, okay? There's no magic here. You have to claim your shared memory yourself. So what do you, and this is it doesn't show it there. This is a pretty big region of memory that it's mapping, right? You want to take a guess on what this is going to be used for? Like, what have we used these giant regions of shared memory for in the earlier challenges?
Shell code.
What's that?
Shell.
Oh, in this module.
In this module.
In this module. We've used it as a communication medium, right? When we will try and read from it and see how long it takes for that memory access to resolve, right? And so we have all of these pieces here of what we've seen in other challenges. We have a region of memory that the challenge accesses somewhere. I haven't found it yet, or have I? The challenge accesses it. And then we saw that I can get this region of memory into my user land process. If I can get it into my user land process, I can time the memory accesses of that same region of memory, which means I can observe or determine which region of memory the kernel is accessing, right? That we're doing that same incrementing and timing, right? Memory access time, memory access time. That is what this shared memory region is for. That's why it's huge. So the real question is, how do I get this device ioctl to then speculatively access that region of memory? It's going to be by calling device octal, by deciphering some of this, and figuring out what you can get this to do. Can you get this to access that region of memory in a way that informs you from user land about what it did? So the only real difference here between Spectre v1 and Spectre v2 is the mechanism by which you are getting this thing to speculatively execute. In Spectre v1, you had this nice little, if the number is really big, we don't do it. If the number is really small, we do, right? Or Maybe it was the other way around. But anyways, you had this nice binary true false, right? And so you could just say true, true, true. We're going to try false, and it would just speculatively fire it. Here, you don't have a nice, clean if else binary. This is what I need to train. Instead, you have this weird call target thing that is an indirect call into a memory location that will or will not access something. And that is what you need to be training.
It's doing the training for you.
Is it doing the training for you?
While
Do I have to actually read this code? If private data 1. Oh, damn. We're going to reverse engineer this whole thing. Don't you give this thing away, all right? I hand waved this thing. All right. I don't want to go any further because we'll accidentally solve it. But yeah, there is this like if something, right? And we know something about this private data that we've talked about, right? A little bit of reverse engineering isn't going to kill you. Do you feel better about it? You can do more work now. All right. I'll take it. I'll take it. I'm worried if I go too much further that it'll just fall out. And then I have to like banish this video, right? And then that's no good. Okay. Anyone that have any other questions there that doesn't involve me accidentally telling you exactly how to do this? It all just looked like spooky stuff. That's fine. That's why you guys have extra credit. You don't have to solve it, right? Post another couple good memes. Okay. What I was going to ramble about, though, my plan. Let's see. Does Twitch have anything? Nah, Twitch is chill. Is levels 13 and 14. If you're trying to optimize, now granted, I get that you get the extra time. It's not live on the dojo right now, but I'll change it after class here, the due date, what I said. If you're trying to optimize for easier solves, it is worth taking a quick look at 13 and 14 before, I think, 10, 11, 12. Yeah, 10. Yeah, 10, 11, 12 are going to be tough. So like 9 had this spooky looking weird IDA stuff, but it was very straightforward code. Like everything that was there for a reason. 10, 11, and 12 have you do Spectre v1, but now you're doing that inside of the on85 VM. So now you have to find the thing that you need to speculatively cause that speculative branch. Find the branch that you can speculate against to get it to happen. It is a slightly modified Yon 85. So like if you are familiar with how Yon 85 works, you should be able to identify these like new pieces of code or functionality, which will give you an idea of where to look. So then we have V1 and then V2 in the Yon 85 VM, right? And so V2 is about changing the pointer of what's being executed, right? Changing that address. And so you would want to apply that same logic here with the Yon 85 implementation. Somewhere there is an indirect call that you can, that's not a good sign, that you can train to execute one way and then switch it up so it will execute something else. An important thing to keep in mind when you're thinking about Spectre v2 is that the arguments stay the same, right? And so what that means is something that is, for instance, an unsigned int64 to one function could be a pointer in another function, right? Or something that is a unsigned int could be a signed int in the context of another function, right? Because the bytes that are being passed as arguments to one function are being misinterpreted or reinterpreted by that function that you're speculatively executing. And so that's something to keep in mind. But the last thing I did want to ramble about was the meltdown challenge. Has anyone got here yet? I don't blame you. So if you haven't done them, the meltdown challenges do require you to connect to the VM. It also makes sense for the kernel module. You probably need to connect to the VM, right? But the meltdown challenges. It was probably, do we have a kernel module there? We do. The meltdown challenges you also need to connect to the VM. Now, level 13, you're just trying to leak the flag from the kernel module's memory. Remember when we talked about, or we had the, what was it, the kernel module where you were going to, I don't want to commit cred. Yeah, we had that task struct thing, right? We had the challenge where it forks off, it deletes the flag and then forks off. And then it deleted the flag, forked off, and that thing died, and you had to find it in memory. So I'll do level 14 so we can see it. 14 is more fun than 13. Maybe. Okay. We take a look at the challenge directory. We have a kernel module and we have a challenge. So, or a user land binary. And when we run the user land binary, hopefully, oh, it doesn't even print anything. That's way more lame. All right. Well, I'll tell you what it does. Why don't I get to see that there? You want to VM connect and demessage?
I'll check demessage.
Demessage says kernel misuse the kernel in a way to teach you about microarchitectural exploitation, blah, 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 pwn.college. Meltdown mitigations are disabled for this challenge. And it tells you that there's two ioctl things that you can do to interact with this kernel module. You can touch a memory address and then get the address of a process's task struct by PID. Okay, well, this challenge opens up the flag and then reads it into memory. And what Meltdown, does Meltdown allow you to access other processes' memory? Nobody watched the video because they haven't gotten there yet? What's that? Yeah. So Spectre is all about measuring that access, measuring that cache timing based upon what you can get another process to do, right? You need this Spectre gadget, right? You need that weird flag byte is an index into an array into some shared region of memory, and that region of memory is your battleground, your communication medium. Meltdown is violating a different security boundary. Meltdown is violating the security boundary between user land and the kernel. Normally, if I have a user land binary, can I access kernel memory? No. What stops me? You say permissions. Okay. It's not a wrong answer. Can you got it?
Memory is not mapped.
What's that? Okay, so the memory is not mapped. That's kind of, sort of true. So, and it's actually it's a great answer, but you probably don't know why that's a great answer. And that's okay. All right. Like at some point, someone will watch these amazing lecture videos of mine. And is this, yeah, okay. If I keep plugging along here, hopefully, oh, I don't have a cool diagram of it. I thought I did. Okay, so before Meltdown was released, right, this was a known vulnerability. It would actually be false to say that the kernel memory is not mapped in your user land process. It would be correct to say you don't have permissions, but it was in fact mapped because it was a performance optimization that when we switch to kernel mode, we already have those addresses in our lookup table, right? And so as a mitigation to this, what they did is they made it so that there's way less kernel memory mapped into user land processes. You still couldn't concretely access it, right? But what Meltdown violates is I could never concretely access kernel memory, right? Like that would always fail. The exact reason could have been permissions. Nowadays, it's because it's not mapped on a reasonable compiled kernel or reasonably configured kernel. But what we could do with Meltdown is we could speculatively access kernel addresses. Now in Spectre, we needed to make the challenge do something, right? We have to ioctl the kernel module and like, yeah, challenge, go use that byte to touch our shared memory, right? But in Meltdown, we don't have to do any of that. So, see if I can find what I was scribbling together earlier today. Melt. There's no need to take screenshots. This is all ripped from my own videos, so you can watch the original where I actually explain what all this code does. Now, the idea here is this secret page would be kernel memory. Right? I'm not actually using kernel memory here because then I have to make the example way harder. But we can imagine that this secret page is kernel memory. And it's just chilling there. I'm not going to ask the kernel to access the secret page. I'm not going to trigger any functionality. There's no ioctl. There's no kernel module. This is all just my own code trying to touch itself. Now, I said at some point earlier in this class that you can actually catch a seg fault. And that is what I'm going to do here in this example. So I wrote a function that is called segFaultHandler. It doesn't really matter. The only thing that it does is it long jumps, which is essentially a goto. Right? It's a prettier way of writing a C goto, which you should never do. And so every time I segfault, we're just going to go to wherever buff is. And we see there is static jump buff. So this is just some address. Every time I segfault, we're just going to reset rip. It's going to go somewhere that I have defined already. Now, what I'm doing here inside of main, this is if I pass an argument to this thing, then we'll register the segfault handler. If I don't pass an argument, then we don't register the handler. This part here is setting up memory, which is pretty not very interesting, but we can show it just for completeness. It's going to mmap, and then we set up the secret, which is going to store the value secret message onto that page that has been mapped. Ooh. All right. And I'm going to loop 14 times and call exploit. That's all you have to do, then it's done. Okay. Now, this exploit is going to be doing the same kind of thing that you've seen already, where we are flushing a buffer, we are speculatively accessing something, and then we are getting timing data. Right? I wrote this slightly differently. I renamed some things because in the original video, I think I called it pre-work and pre-work and pre-inner work, and you should never use function names like that. Right? I wrote it like the night before and have regretted it for 3 years now. So I'm going to flush the buffer 100 times and then try and speculatively access some address here. And then I'm just summing these metrics. Now, one of the things that you probably want to know is how am I speculatively accessing it? Because in Spectre, I had to ioctl, I had to sem post, right? I had to trigger the challenge to go do this memory access. It was the challenge that was doing this speculative thing. In Meltdown, I'm doing my own speculating. I'm doing my own speculating over to some region of memory that I am not allowed to touch. And so how do I force myself to speculate? There's a number of ways you could do this, but I think this is a clever one. So if you haven't seen this very crazy syntax, you're a luckier person before today. This is known as a GCC extended assembly syntax. It is a way of inlining assembly and having it relate to your C variables. right? So you can take your C code and you can link it down to assembly and then have the results pop back out into C. And so you can write code that does both in one and it all compiles together. The way to interpret this is just assembly, and that's great. This first colon is the output variables. These are the things that are being output to. In my case, I output to nothing. So that works out. The second colon defines the variables that are input variables that we're going to be reading from. There's also these little character codes that define how you're interacting with that variable, whether it's like a pointer to something or it's a literal. Because we have, like, if I don't know, in this case, target address is a pointer, it's a char star, but we could have been like, instead of reading it as or treating it as a pointer, I'm going to treat it as a literal, right? I don't have the syntax memorized, but you can look it up, and these characters define how that value is being interpreted, whether we're abstractly dereferencing it or treating it as a literal value. Somebody says, that's bonkers. It is assembled by the same assembler that assembles. That's a lot of assembling. Is it assembled by the same assembler that assembles the object code that C spits out? Yes, it is still assembled by GCC. That is why it is the GCC extended assembly syntax. So I'm saying that I want to read in from target address and com buffer, which in this case are just two char stars. I'm just treating them as abstract pointers. I don't really care. This third colon defines the registers that this assembly is going to clobber. That was a face. You're not familiar with the term clobber? It's a great word. All right. Anyone want to tell me what clobbering is? Come on, Jan says clobber all the time. This is a good old 365 thing. It's memory corruption. We did memory corruption. Clobbering is when you corrupt something, right? You change the value, you mess it up. And so I have to define what registers are going to be messed up by this assembly because the compiler doesn't know what I'm doing, right? The compiler's just like, yep, this assembly is going there, but the compiler has to figure out what to do beforehand and then after to make sure this doesn't explode. And so I'm telling the compiler I want to read in these two values, which are both pointers to memory addresses. And along the way, I'm going to mess up the registers RCX, RBX, and RAX. All right. So that was some good time. Let's look at the actual assembly. I'm going to clear RAX, and then I'm going to load the effective address of %1 into RBX. Anyone want to take a gander what this percent nonsense is?
So target
address. Percentage
We guessed target address. It is in fact zero indexed because we are rational people. All right, we live in a society. There are rules. The %1 refers to the second argument there. And so we're going to load the address of the COM buffer into RBX. I'm then going to move 1337 into RAX. I'm going to push that value onto the stack. Now this is a little bit weird. This is a floating point load from RSP. And then SQRT is a floating point square root. It's weird. I'm doing floating point stuff again. We saw me do weird floating point stuff last week. Why did I do weird floating point stuff last week? Am I making it busier?
No way, like floating point instructions take longer to process.
Okay, so floating point instructions take longer to execute. Okay. And then this right here is a floating point store. So we're this first one here is taking the value that's at RSP into this floating point, bringing it into floating point land. We're doing a floating point square root on it. And then we're bringing it back to kind of our sane land of assembly that we know and love. Now, is there a branch here? Okay. So there's no branch. Is there an indirect call? You're saying somewhere? No, there actually isn't. right? This isn't Spectre V1 or Spectre V2. I said we're going to talk about Meltdown. You could have just said no, fool. But it is slow, right? Does the CPU only speculate at branches? No. Does the CPU only speculate at indirect calls? No. When does the CPU speculate?
When it is waiting for something to finish, waiting on something.
So the statement for Twitch here is when it's waiting for something. It does speculate then. Is that the only time that it speculates?
RAX value, it is dependent on the entire calculation thing that you're doing in the above assembly instructions. So I'm assuming that at that point it can't speculate since it doesn't have a value. Yeah.
So this may have been a trap on my side. So I'll close it. The CPU is always speculating. Normal execution of the CPU is out of order and is speculating. It doesn't matter if this is slow or this is fast. The CPU is in just as assembly instructions come in and it's breaking it down. It's building this dependency chain. It doesn't matter how slow or fast there are. We have more computational units that can run things, and we're going to keep processing stuff ahead of where RIP is, regardless of whether it's slow or not. We're going to be executing stuff early and later at the same time. Why? Because we have the cores, or not necessarily the cores, but we have the CPU components to do it. So the CPU speculates all the time, not just at branches or not just at indirect calls. And so the CPU is speculating right here while I'm doing this. Now, we said that floating points are slow. All right, so that's going to be slow. We're going to pop RAX. This is going to get me the result of that square root. Then I'm going to move that value into RAX as a pointer, which is pretty much guaranteed to segfault, right? Because we're just like arbitrarily being like, yeah, this floating point square root number is going to be an address, and we're just going to try and write there. So I've written something that guarantees a segfault. How about this nonsense? Should this ever actually execute concretely?
No.
Concretely, it will never execute, right? Because I will always segfault here. Does the CPU know that? No. And so the CPU is doing its normal, regular, speculative execution. Just, yeah, man, this is what we do, right? Cool, you got this floating point number. While you're at it, we're going to do this work down here. What is this work down here? We're going to move the byte that is at the target address into CL. We're then going to bit shift that to the left by 12. Why am I bit shifting it by 12? Yes, 12 bits is a page size. So I'm doing that same thing. So I said every challenge here, the shared memory kind of multiple that we're going to use is always going to be a multiple of a page. So I'm reading in the byte that I need. I'm shifting it to the multiple of a page. I'm then adding that to a base address, RBX, which RBX was the base address of my COM buffer that I started way up earlier. Because I might as well set up the COM buffer before I start speculating, right? Let's get the work that I know I have to do that doesn't mess anything up done early. And so I'm going to add, for this would be index 0, whatever my byte is, pages into it, and then I'm going to access it. And that would be a speculative access. And I'm doing it to myself. But I'm always going to segfault. So then this blows up and then it's all over, right? Don't run the compiler in the VM. So I wrote that in Intel syntax. Oh no. Let's see if I have it chilling in here. MASM, not March. Someone says speculate early and often. I'll take it. All right, so this is going to segfault. Why is it segfaulting? Yeah, that is what we expect, because if I didn't pass an argument, I didn't put the segfault handler. I just wanted to prove that it actually does segfault, right? Like this wasn't meant to be a big trick there. Now, if I pass an argument, let's open up melt.c. So down here at the bottom, if I pass an argument, then we register the segfault handler. So I'm still segfaulting. It's just, it's going to that segfault handler that is then jumping back and restoring things instead of just blowing up. And so that allows me, if we look at my speculative exploit here, where is my segfault handler? We said we're going to long jump to buff, and buff is getting set inside this loop. So this 100 iterations isn't actually looping around, is it? I'm segfaulting 100 times, and then I'm jumping. So I go into here, I segfault. I then jump back up to here to segfault all over again. This is just 100 segfaults really fast in one process. And then I'm measuring the access times across them. And what we see here is I can then leak the secret value. It's kind of spaced out, but secret_MESAGE, right? It's still a speculative side channel attack. The difference with Meltdown is that I don't need to trigger this behavior in some other process that is holding the secret value, right? Now, for this example, technically it isn't Meltdown, but I am using the very, very similar code to what you would do for Meltdown. But in reality, I'm leaking the secret page, which is still in user land, that's mapped in my own process. For it to be Meltdown, I would just need to change my target address from being this secret page to being some address that is in the kernel. All right. And the reason that this works is actually different. It's slightly different than Spectre. So inside the, where is this? I'm just not going to say it because I'm going to be wrong. There's this thing called the supervisor bit, right? That is what determines whether you are the kernel or not. It's literally just a 0 or 1. When you try and access a memory address that starts with an F there, and so it's in kernel space, that is what is checked as the supervisor bit. And so the reason that Meltdown works is because the speculative access bypasses that supervisor bit check, which is different than Spectre, which is causing another process to speculatively access memory and then taking advantage of the side channel that can be observed. They're very similar, right? It's kind of a hand wavy, oh yeah, but it all uses flush and reload, right? There's actually more ways to deal with the catch and flush and reload, but flush and reload is the most straightforward way to take advantage of it. So it's slightly different because we're accessing kernel memory, and what we're bypassing there is this supervisor bit check for accessing kernel memory. And so we're doing this all from user land to create a speculative scenario to then leak memory from the kernel. But for this level, because I said this is a cool level, level 14, it's not very clear how I get the flag, right? Because it's not very helpful. So if we take a look at this user land binary, what we'll see mash tab. It's pretty interesting userland binary here. We're going to open the flag. We're going to read the flag, and then we're going to busy loop. That's all this userland process does. Does Meltdown allow me to access this process's memory directly? No, we said Meltdown violates the supervisor bit into the kernel. All right. Well, what do I know about the kernel from the kernel module?
It can access any process's memory.
Okay, the kernel can access any process's memory. How should I do that? So Meltdown gives me this primitive where I can like read bytes from the kernel wherever I want.
So maybe the kernel module can read the flag from this process's memory, and then we can use meltdown to read from kernel's.
Okay, so the thought was maybe I can get the kernel to read this process's memory, and I use Meltdown to read it back from the kernel. That's a fair thought. It's not the answer, but it's a fair thought. We haven't taken a look at the kernel module. I think that'd be too easy for a level 14. For the last level of this legendary module? Come on. So, init module, what do we got? Nothing super exciting. Device open. Looks super useful, right? It's gonna give a 0.
I mean, I don't trust IDA to decompile kernel modules at this point.
You don't trust what? How do you not trust IDA?
For kernel modules.
I am shocked. So the D message that we looked at, that's a good idea. I don't remember if it's this challenge or another one, but there definitely is a challenge here where if you mash tab and look at the decomp in IDA, there'll be things that are empty.
It's 8.
What is it?
8, level 8.
Level 8? Yeah. You'll IDA will decomp it into nothing. But then if you look at the assembly, there's actually stuff going on. It's just IDA can't make sense of it. I think somebody said, I don't know this to be true, but somebody said Binja does an okay job of that. Binja and anger management, way better than IDA. Heard it here first. So what we can do in this module is going to be what it said here in the D message, right? We can call device ioctl on this. And depending on the command that we pass to it, we will be able to, let's see, copy from user. It's going to find a PID. So we get to pass a PID to this thing, and it is going to give us the address of the task struct for the PID. So I could give it 1, and it's going to give me the address in the kernel of the task struct for PID 1. Is that the flag? No. Okay. What else can we do to this thing? There was something else up here I skipped. Ioctl param fu list next. What did D message call that thing? Touch a memory address. So we have the ability to touch something, right? Because this is essentially just a memory access. And then we have the ability to get the task struct of an arbitrary process. So what do I need? What do I know about task structs? They are complicated, right? I'll give you that, but where can we figure out how they work? Okay, GDB is one place. I think I went down the rabbit hole of the task struct back in the kernel module, right? Yes, kernel documentation, although documentation, no, there is documentation. Like, I'm sure it's documented somewhere.
I couldn't find it.
I don't know how good the documentation is, but what you can find is the source, right? It's the power of open source. Here's our task struct. Hopefully I picked the right thing. Otherwise, someone will for sure point it out to me on the Discord. for the next year. Somewhere on here, at some offset from the beginning of the task struct, is going to be, see if I can find it, the first step to dereferencing virtual memory, which I added. So somebody called me out. I should really point this out in my last few moments. Oh no. Okay. I accessed this from Bluebelt. If you access this from the course, I added further reading back when I added this. A super useful link for 14 is this last one here, which is a blog post by one of the graduate students here at the SEPCOM lab. It's a write-up on, remember where Jan talked about there's CR3, then there's the page, then we do this math, and we go into this next page to turn virtual memory to physical memory. Well, this is a write-up that explains how that mechanism works. And you can get to this page table from the task struct. So your strategy here is going to be to get the task struct address, to then leak the page table, to then do some math, to leak the, I guess, page middle directory. They're all page tables to me, right? The PMD, to then get to the PUD, to then get the PGD of that task, which is the challenge that holds the flag. And that would allow you to translate the virtual address of where the flag is to a physical memory address inside the kernel to then read it from the kernel. So you're going to have to write Meltdown to take advantage of the kernel, but you're going to have to speculatively navigate the page tables to get to the flag in the physical FizzMap. Because otherwise, like imagine you were trying to do what you did in the kernel module, where you started beginning a FizzMap and you're just like, yeah, where is it? But now you have to do that speculatively, one byte at a time. It is less work to actually figure out where it is on FizzMap. And so that's what 14 is. But 30, it sounds like a lot. But once you get cracking at it, it's not that bad at all. 13 and 14 are generally considered easier than 11 and 12, and some people would say 10. So if you're trying to optimize for ease of solves, definitely give them a look. All right, with that, I will leave you guys. Twitch, it was fun hanging out. I hope everyone has a good holiday. Hopefully there's a bit less stress here, at least for me for this week. Goodbye, good luck. I'll see you all on Tuesday.